All right, so let's get started here. Tonight we're going to be talking about environmental and water resources. So this is an overarching, a lot of topics here to cover for this section of the FE review. So basically we're going to be looking here at three different topics. We're going to look at fluid mechanics, hydraulics and hydrology, and environmental engineering. So comprehensively there, that makes up about 23% of your FE exam. So I recently looked up, these are kind of the highlights of the points that you can be tested over in each of these different topics. And so for fluid mechanics there, you can see we could have general fluid properties, flow measurement, so they're using Bernoulli's equation to measure the velocity within a pipe or the pressure. You could have problems on fluid statics, energy impulse and momentum equations, and we'll go over some examples that cover that. Hydraulics and hydrology, mainly I'm going to cover a couple examples in the hydraulics. So here you could have basic hydrology, basic hydraulics, pumping systems, municipal water distribution systems, reservoirs, a lot of use of Manning's equation and the Hayes and Williams equation here. Okay, so I have an old FE exam that I've kind of used as a tool here and to pull problems from, and mainly they were testing for the hydraulic section over Hayes and Williams and Manning's equation. And then the environmental engineering section, here this is primarily going to be water, wastewater. Okay, so the old exam, when I took 5 years ago, roundabouts, it also had air quality, a good amount of air quality, and solid and municipal waste management. But now, the new regulation, I looked earlier today at the 2014 exam, and those two things were removed. So I think they're not as prominent now on the exam. Maybe they're not required. So here, water quality, basic tests for water and wastewater, some tests for air maybe. That'd be about the extent of your air quality that you'd be tested over. Environmental regulation, and then water and wastewater treatment design are the primary things you could be looking at there. So let's jump right in. I have about 11 examples there in your packet that we're going to cover. Start first with that fluid mechanics section. Jump into a problem with the ideal gas law. Okay, so this problem states that you have a volume, or you want to calculate what the volume is of 1 mole of water at 546 degrees Kelvin in 1 atmosphere. So this is likely, this is probably done with water vapor, right? Because the water itself, it's a liquid, not a gas. So this is probably applying to a water vapor. So we want to calculate what that volume is going to be. We see there that the equation that we use for the ideal gas law, there's 3 main equations, or we can rework, modify the equation a little, but generally see that, look here, that PV is going to be equal to N times RT. Okay, so here it's going to be temperature. This temperature is an absolute temperature. So what that means, it's going to be in either Rankine or it's going to be in Kelvin. Okay, so in our problem statement, we're given it in terms of Kelvin. And we're given that it's equal to 546 Kelvin. This R value here, this is going to be our universal gas constant. Okay, so this would be given in your reference material. Gas constant. And this has a value of 8.314 joules per mole times Kelvin. Okay. And your N term here is going to be your number of moles. And for our problem statement there, we're told that we have 1 mole of water. Pressure, so this term in this problem is a little tricky. So it gives you pressure as 1 atmosphere. Okay, so 1 atmosphere is going to be 101.3 kilopascals, right? So we have to be careful with our units here because everything else, the way the units would cancel, we see that we need to convert this over to pascals instead of kilopascals. So that's going to be 101,300 pascals. Okay? So we can apply the ideal gas law there to solve for what that volume is going to be. So that's going to be volume equals nRT over our pressure. End up seeing there that that's going to be equal to 1 mole times 8.314 joules per mole Kelvin times 546 degrees Kelvin over 101,300, sorry, it should be pascals. Okay, so what we end up getting here is that this volume is equal to 0.0448 meters cubed. Well, we see there that they want the volume in terms of liters, so we know that there's 1,000 liters in 1 cubic meter. End up getting a volume there of 44.8 liters. So the correct answer there should be D. Any questions on that problem? So you could also be given this in terms, let's see here, maybe you're given the density, or you're given, maybe they want you to solve for the number of moles. So basically you can rearrange and rework this equation in a number of different ways, and they could ask a number of different problems associated with this. But you'll probably see at least one ideal gas law problem on the FE. All right. So moving on there. Second question here is on hydrostatic. So we're looking at hydrostatic forces acting on this gate. That's going to create a moment, a clockwise moment on this gate. And we want to know what that resultant force, or the magnitude of the force required to keep the gate closed. Okay? So let's see, we're given that it's a rectangular homogeneous gate with a height of 3 meters and a width of 1 meter. We're told that it's a frictionless hinge at the bottom. Okay, so we know there's not going to be a moment associated with the friction about the hinge. So, and we're given the density of the fluid as 1,600 kilograms per meter cubed. And so we know that that hydrostatic force, we can look at that pressure distribution acting on that gate. So we know that hydrostatic, or that pressure distribution there is going to create a resultant force. Okay? Where's that resultant force going to be acting there? In reference to the hinge. How far from that hinge? You guys remember? It's going to be a third of that height, right? So that moment arm associated with that resultant force is going to be 1/3 of the height. Okay? So let's work through this problem here. If we take a sum of the moments about that hinge, we want to know when it's what magnitude of that force we need, basically right when it's about to tip. Okay, so we want to know when that's the sum of those moments about that hinge are going to be equal to 0. So the force associated, or the resultant force associated with that fluid, is going to create a clockwise moment. And so we know it's going to be that times 1/3, 3 meters, so 1/3 of the height is going to be the moment arm there. And the moment associated with that magnitude of the force to keep the gate closed is going to have a moment arm there of 3 meters. It's going to be set equal to 0. So we can rearrange this equation here. We can say that the force that we're interested in is going to be the resultant force of that fluid divided by 3. Okay? So that resultant force is going to be equal to the gamma of the fluid. Remember, we're given density, so gamma is just going to be rho times g times h over 2. So why am I multiplying by h over 2 there? Right. Right. So we see there, we multiply that by h over 2 times 3 meters times 1 meter. So this is the cross-sectional area of that gate. We can divide that by 3. So we end up seeing there is that this force is going to equal the density, 1,600 kilograms per meter cubed. There's gravity, 9.81 meters per second squared. Again, here we have to multiply by gravity to get the gamma of the fluid, or the weight of the fluid, times 3 meters squared. So this is going to be that cross-sectional area of the gate, times h over 2, which is going to be 1.5 meters. Again, we have to divide all this by 3. So what we end up seeing there is that this is going to equal 23,500 newtons, or 23.5 kilonewtons. And so 23.5 isn't an answer in your problem statement there, but it says the closest one to it is going to be 24. So we round up there, and we see that the answer is C. C. All right. So moving on, we got a couple more here in the fluid properties, or in the fluid mechanics section. It's kind of a conceptual question that they had in the exam. It says, which of the following statements is true of viscosity? A, it is a ratio of inertial to viscous forces. B, it always has a large effect on the value of the friction factor. C, it's a ratio of the shear stress to the rate of shear deformation. Or D, it's usually low when turbulent forces predominate. So does anybody remember what Newton's law of viscosity says? So we can use Newton's law of viscosity here to say that the shear stress is going to equal viscosity times du dy. Okay? So this is going to be shear stress. And this is going to be the rate of shear deformation. So we can see there that mu is going to be the ratio of shear stress to that rate of shear deformation. So we see there that answer is going to be C. So A, the ratio of inertial to viscous forces. Anybody know what that is, or what that's going to be? This is actually Reynolds number. Okay? So VD over the kinematic viscosity. So your VD there, that's going to be your inertial forces. So you could easily get a question of which of the following statements is true of Reynolds number, and the answer there would be A. And this is going to be kinematic viscosity. Okay, any questions on that one? All right, moving on. So obviously there we covered hydrostatics, covered a problem there on fluid properties. I saw something on the ideal gas law as well. Some other prime topics that you could see from fluid mechanics would be application of the momentum equation, which we'll do one of those here. Again, Bernoulli's equation and the continuity equation. Okay, so in this example, we see that we have a horizontal jet of water with a density of 1,000 kilograms per meter cubed. This would be the density you would normally assume for water if you were working through these problems and it wasn't given in your problem statement. It is deflected perpendicularly to the original jet stream by a plate as shown below. It wants to know the magnitude of the force required to hold the plate in place. And so what we see here, what we need to do with these types of problems, the first thing we want to do, we want to draw a control volume for the fluid. So we draw a CV for the fluid. And in this case, we see that our jet is deflected here by this plate. And so we can choose our control volume here. I'll do that in another color to encompass our inputs and outputs. All right, and so here we're going to have our momentum, or our rho QV coming into the system, or into the control volume from the flowing fluid. We're going to have this external force that's holding that plate in place. So this is going to be the normal force exerted by that plate on the fluid. We're going to have this rho QV term out of the control volume, and this rho QV term out of the control volume as well. So what the linear, we can use basically Reynolds transport theorem to derive the linear momentum equation. So the linear momentum equation what that's telling us is essentially it's applying that conservation of momentum principle to a control volume approach. So using that Eulerian approach for conservation of momentum. We see that the sum of the forces in the x direction, so here we're interested in the x direction because it's an x directional force that is holding that plate in place, is going to be equal to our rho QV out in the x direction minus rho QV in the x direction. Okay, so this is going to be, again, our linear momentum equation. So let's work this problem looking term by term there. So the sum of external forces in the x direction are just going to be, if we assume a positive x direction, this would be our positive x direction, we're going to see that we have this negative external force holding that plate in place, or that normal force exerted by that plate on the fluid. So that's going to be equal to negative F. Okay? Does everybody see that? Our rho QV out in the x direction is going to be equal to what? So what that momentum associated with the fluid there from in the x direction leaving the control volume, it's going to be 0, right? And our rho QV in the x direction is going to be equal to our density, 1,000. Here we see that rho QV coming into the control volume in the x direction. 1,000 kilograms per meter cubed times, all right, so Q is going to just be velocity times the area, right, the cross-sectional area. And we're given in the problem statement there the jet area as 0.01 meters squared. So this is going to be 0.01 meters squared. And then we multiply that by the velocity of 30 meters per second. So we end up seeing here this is going to be equal to 9,000 newtons. Okay? If we go back and plug in our original equation, so here we derived each of the individual components for that linear momentum equation, we can say here that negative F is going to be equal to 0 minus rho Q V in the x direction. Okay? So basically there we see that we can say that that force is going to be equal, those negatives cancel out, force is going to be equal to negative rho, or positive rho QV in the x direction, which equals 9,000 newtons, or 9 kilonewtons. So there we see that our answer is going to be equal to, or going to be B for this question. So you got to be careful there with the units. So you see D is 90 kilonewtons. So you got to be very careful here when you're working them and check on your units as you go throughout the problem, because it'd be very easy to make an order of magnitude mistake when you're working through these. All right. So our last problem here from the fluid mechanics section is going to be an application of Bernoulli's equation. So we see there we have a pitot tube that's placed at a point where the velocity is 2 meters per second. So if the velocity in this stream or in this pipe is 2 meters per second, is it going to change at all as it moves through the pipe? So is our velocity here, is it going to change? Obviously here at the pitot tube, we're going to have a stagnation point, right? But other than that, are we going to have any change in our velocity within this pipe?
Yes.
Why is that?
Frictional loss.
So we can assume here that we can neglect frictional losses, if you neglect frictional losses here. So this is just a pure application of Bernoulli's where we assume that friction is negligible. Okay, okay. So basically we can use that continuity principle here. We see that we don't have a change in area. So our Q in is going to be equal to our Q out. And so since the area of this pipe isn't changing, that velocity has to remain constant throughout. Okay? Does that make sense? Okay. So we can apply Bernoulli's equation here at 2 points. So we'll call this, if we have a streamline that runs through the center of this pipe, we'll call the stagnation point of this pitot tube, point 1, and then directly under this other arm of the manometer will be point 2. So we can apply Bernoulli's equation along that streamline. What that says is that P1 over gamma plus Z1 plus Z1 plus V1 squared over 2G is going to be equal to P2 over gamma plus Z2 plus V2 squared over 2G. Okay? So we can start canceling out terms. For the first thing we want to do when we work a Bernoulli problem, we want to cancel out stuff that is easy and we already know. So we see here, this is a horizontal pipe, and so along this streamline, we're not going to have an elevation difference. Since we have 0 elevation difference, we can say Z1 and Z2 are equal to 0, or the difference between Z1 and Z2 will be 0. Okay? So point 1, again, there was the point in the streamline where we hit the stagnation point. So at that point, our velocity is going to be equal to 0. It's transferring all that kinetic energy to a pressure head. Okay? And so our velocity in that point will be 0. We can also say, we're given a manometer here. And so we can say P1 is going to be equal, we can use our manometry equation here, is going to be equal to P2 minus gamma of the fluid times some distance d. And so this distance d here, I'm essentially defining as distance between that elevation and the streamline. So this is point D, some arbitrary value. We'll see later that this cancels out, but I just wanted to give it a definition for now. And we subtract gamma of air times H, and we can use the fact that the change in pressure with respect to X for that static fluid in the manometer here, the pressure at this point will be the same as the pressure at this point, so we can move over there in our manometer, and then we can say plus gamma of the fluid times H plus gamma of the fluid times D. We see here that our gamma fluid times D cancels out, And we can say here that gamma air times H, the specific weight of air relative to the specific weight of fluid is going to be really small, right? The density of air much, much less than the density of our fluid. So we can say that this term is pretty much 0. So what we end up seeing there is that our pressure difference, P1 minus P2, is going to be equal to the gamma of our fluid times H. Or H is going to be equal to P1 over gamma minus P2 over gamma. Okay? So if we move back into Bernoulli's equation, we can see that we can rearrange here with this identity that H is going to equal P1 over gamma minus P2 over gamma. And we can say that V2 squared over 2G is going to be equal to H. Okay? So H, we're given the velocity as 2 meters per second in that pipe. And so H is going to be equal to 4 meters squared per second squared. Remember that velocity is squared, divided by 2 times 9.81 meters per second squared. We end up seeing here that we have an H of 0.2 meters. Okay? So there our answer was going to be D. All right. So any questions on that? That pretty much covers fluid mechanics. Oh, and you know what? I'm not sure. That'd be easy enough to calculate. So let's see here. Does anybody have a calculator on them? Okay. So go ahead and multiply that by 9.81, and then you can divide it by 32.2. Okay, so that's not one of them on there, but they will do little things like that. So a lot of the ones you notice, you notice some unit conversions. We'll see that later on in the environmental section. Basically, if you don't convert your time units to the correct units, you can see you would get one of the answers. So you will see that pretty often. I'm not sure what the tricks are on this one. Oh, do you? Yeah. Well, yeah, that makes sense. So, yeah, there's little things here and there that could trip you up along the way. So just be very careful when you're working through the problems and check all your units multiple times. I believe that I read from last year there's 110 questions, but I think you have 6 hours to take the exam. I'm pretty sure that's still the component. Is everybody here taking it? Is it January? Okay. All right, so let's move in and work a few hydraulics problems. So here we're going to be working a couple of Manning's equation problems and Hayes and Williams problem. So in this problem, we want to calculate the velocity using Manning's equation. So we're given that we have a 12-inch diameter concrete sanitary sewer with a Manning's N coefficient of 0.013. So this is going to be constant with depth. We're told that this pipe is flowing half full and is constructed on a grade of 0.5%. The flow velocity in the sewer is most nearly going to be what? Is what it wants you to solve for there. So we can go ahead and write down Manning's equation. So it'll either give you Manning's as in terms of Q or velocity. You know that Q is going to be equal to K over N, and this is a constant. K is a constant that accounts for which unit system you're in. So it's K over N times A times R to the 2/3. R there, that's hydraulic radius, and A is going to be the cross-sectional area of the fluid in that pipe times S to the 1/2. So this is going to be your bed slope or your friction slope. in open channel flow. So we can say there the problem statement wants velocity, not flow rate. So velocity, we can just divide by area. End up seeing it's going to be K over N, R to the 2/3, S to the 1/2. Okay? R, that hydraulic radius, what's that going to be equal to? You remember from hydraulics. Anybody remember? So hydraulic radius is going to be equal to the area divided by the wetted perimeter. Okay? So the wetted perimeter is going to be basically the length that that fluid is in contact with your sewer. Wetted perimeter. So let's see here. For a 1-foot diameter pipe that's flowing half full, see that the area is going to be equal to pi r squared times 1/2. Again, it's flowing half full, so we have to multiply by 1/2. See that this area is going to be equal to 0.39 feet squared. Our wetted perimeter is going to be equal to pi d over 2. So this is going to be the circumference. Pi d is going to be your circumference. And we have to multiply by 1/2 since it's flowing half full. So this is going to end up equaling 1.57 feet. Okay. K, this is going to be given. You can look this up in your reference manual. For BG units, it's going to be equal to 1.486. And our slope is given as 0.05 or 0.005 feet per feet. So this is an area where you can trip up on this problem because you're given the slope in terms of percent, but you need to convert it there to feet per feet. Okay, so that's how it's derived in the equation. It's an empirical formula, so it's important that you do that. And it's not directly going to impact the answer there, but it could be a reason why they have D on here, this 32.4. The answer ends up being, I believe, C. So they might have that 32.4 there to kind of trip you up in terms of that order of magnitude difference associated with the slope. And so we can plug our values in here into Manning's equation. We got 1.486 over 0.013 times 0.39 to the 2/3 over 1.57 to the 2/3 times 0.005, the square root of that. End up seeing that it equals 3.2 feet per second. Okay, so our answer there is going to be C. You have a question? Oh, okay. All right, ready to move on? So here's another example using Manning's equation. This one has a little trick to it. So we see here a sanitary sewer delivers flow from a sump to a lift station as shown in the figure below. The sewer length is given as 400 feet and the diameter is 30 inches. The sewer is made of concrete and has a roughness coefficient of 0.013. So we want to know for full pipe flow with water surface elevations in the upstream sewer pump and lift station, wet well of 105 and 103.5, what's the discharge? And so here we're saying that the water surface elevation and that sump well and wet well, this is going to be 103.5, this is going to be 105 feet. So what's that slope going to be that we used for Manning's equation? It's going to be the friction slope, right? It's defined as the friction slope. So this is going to be based off of the water surface elevation in these two compartments. So our friction slope there is going to be 105 feet minus 103.5 feet divided by 400. So they try and trip you up a little bit here because you're given the basically the bottom of the pipe. You're given the elevations for that sump invert and the lift station invert where the pipe is coming through there. You're given those as 101 and 100 feet. It was somewhat surprising, but if you plug those numbers in, that doesn't give you one of these four answers. So they don't crush you if you mess that up. But the correct slope here is going to be based off that water surface elevation in those two compartments. Okay, so this is a common theme. I've seen this on, it occurs again on that next problem that we're going to work with the Hazen-Williams equation. But very important here, you're using friction slope. And so if we want to calculate flow rate from Manning's equation, see, we can apply it again. It's going to be 1.486 over N times area times R to the 2/3 slope, that friction slope, to the 1/2. So again, we calculated friction slope there is going to be equal to 0.00375, and this is going to be feet per feet. Okay, so we can plug our values in here to Manning's equation. We have 1.486 over 0.013 times pi. Okay, so this is one of the areas that'll trip you up. You're given the diameter in terms of inches. You need to convert that over to feet. So if you plugged in the numbers in terms of inches, I think it does give you one of the wrong answers. Okay, so make sure you convert. We need to convert over to feet here. So this is going to be pi times r squared, so 15 inches divided by 12 inches per foot. Square that, and then multiply by our hydraulic radius to the 2/3. And so that's going to be pi times 15 over 12 squared divided by pi times d. So circumference is going to be pi d again. Remember, the pipe is flowing full here. So it's going to be 30 over 12. This is going to be raised, all this will be raised there to the 2/3. And then we can multiply by our slope, 0.00375. This is going to be raised to the 1/2. So when we solve here, we see that we get a Q equal to 25.1 cubic feet per second, or feet cubed per second. Okay? Any questions on that one? Give me a second to write it down there. So the correct answer on that one is going to be B. All right, so let's look at our last one here in the hydraulic section. Given a word problem here, so they don't give you any depiction here of this problem. It says that two tanks are connected by a 500-foot length, 1-inch inner diameter PVC pipe. The appropriate value for the Hazen-Williams coefficient, so this kind of triggers you there to use the Hazen-Williams equation, is going to be 150. So if you have water at 60 degrees Fahrenheit flowing through the pipe at a velocity of 10 feet per second, so we're given the velocity of that fluid within that pipe, and the tanks are open to the atmosphere, entrance, exit, and minor losses are negligible, and the difference in water surface elevation between the two tanks is most linearly going to be what? So we want to calculate the delta H between those tanks. So if we draw this system, we can depict this system here. For our two tanks, given that this is a 1-inch inner diameter pipe connecting these two tanks, we want to calculate what the difference here in our elevations in those two tanks are going to be. Okay? So what's going to cause this head loss here, conceptually? What do you guys think? Friction, right? So it's going to be friction in the pipe that's going to cause our head loss here. And if we have a 1-inch inner diameter pipe, then there could be a lot of potential head loss in that system, okay? So a very small pipe. It's going to be moving very fast and very sensitive there to the roughness of that pipe. So if we assume flowing full, obviously it has to be flowing full, right? We can say there that Hayes-Williams equation is going to be velocity is equal to 1.38 times c times r to the 0.63. So you see here this is very similar to Manning's formula. Again, another empirical equation here. Formula. And we can see here just in terms of the roughness coefficient. So here our C value was 150, right? But our Manning's N is normally 0.01 to 0.03, something in that range, right? So you see here that this is multiplied by this roughness coefficient as opposed to divided by that roughness coefficient. Inner diameter. Yeah, so ID, this is going to be inner diameter. Good question. All right, so our R, our hydraulic radius, is going to be area over the wetted perimeter, which is going to be equal to pi d squared over 4 times 1 over pi d. So in general, for these flowing full conditions, we can simplify this as d over 4. Okay? So we can plug back in here to the Hayes-Williams equation. We say that 10 feet per second, our velocity, is going to be equal to 1.38 times that coefficient C, 150, times 1 over 12. Again, here we got to convert from inches to feet, divided by 4. So it's that diameter of the pipe is going to be 1 over 12 feet to the 0.63 S to the 0.54. So we can solve for S to get our friction slope, okay? To get our friction slope. And what we see here is that S is going to be equal to 0.364 feet per foot. So this means that basically for each foot of that, linear foot of that piping system that's transporting the fluid from tank 1 to tank 2, that you're going to have a head loss of 0.364 feet per each foot of that pipe. Okay? So our delta H then is going to be equal to 500 feet times our slope, 0.364 feet per feet, which equals 182 feet. So it's a lot of head loss in our system. And again, that's reasonable there because we have a very thin tube and that velocity is very high, 10 feet per second. That's cranking. That's moving pretty fast. So it's reasonable to think that we'd have that much head loss in our system. So the answer for this one was C. The answer is C. Okay. All right, moving on. Any questions there on the hydraulics? If you have any questions on hydrology or specific questions on hydrology or hydraulics, there were none in the sample exam that I had to present for you on hydrology. Please feel free to come or to email me, come to my office, ask me about them, and I can help you out with them the best of my ability. So when you're studying, you come across something that you don't remember how to do, just let me know and we can work through it. So, All right, so let's move on now to environmental engineering, the environmental engineering section of the exam. First question that we have here, we're looking at basically what the oxygen demand is going to be to biodegrade benzene. So this is a carbon-containing structure, organic matter here, to CO2 and H2O. So the question says you're designing an aerobic system to biodegrade this benzene, and it gives you the chemical reaction there as well as the atomic weights of each of the elements. If you have a benzene concentration of 500 milligrams per liter, it wants to know the concentration or the amount of oxygen that's going to be consumed to completely biodegrade the benzene. Okay? So the first process or first step we need to do here is we need to balance this equation. So we see C6H6 plus O2 is going to yield CO2, carbon dioxide, plus H2O. So go back into your chemistry toolbox and we're going to balance this reaction. So the easiest way to do this here, we see that we have carbon containing this one compound on the left-hand side and this one compound on the right-hand side. So we know that we're going to have 6 moles of carbon dioxide per mole of benzene there in order to get the appropriate amount of carbon. As well, we see that hydrogen is contained here and contained here. Those are the only 2 compounds there that contain hydrogen, so that means we have to have 3 moles of water in order to meet that or balance that hydrogen requirement on the left-hand side of the equation. So finally, we see that we have oxygen occurring multiple places here. So we have 2 atoms of oxygen on the left-hand side, and then we have, let's see, 12 associated with CO2 and 3 that are going to be associated with water. So to balance this reaction, we see that we're going to have 7.5 moles or 15/2 moles of O2 in order to balance the oxygens that are on the right-hand side of the equation. Does everybody see that? Does that make sense? Okay. All right, so we can use, now that we have a balanced reaction, we can use the stoichiometry of this problem to answer how much oxygen is going to be required there to completely degrade or biodegrade that benzene. So see that it takes 7.5 moles of oxygen per 1 mole of benzene. Okay, so if we have 500 milligrams per liter, milligrams of C6H6 per liter, we can convert that over to a number of moles of benzene. So in 1 mole, we're going to have 12 times 6. We need to get that molecular weight there of benzene plus 6. This is going to be times 10 to the third. So this is how many milligrams of benzene we're going to have in 1 mole. So that's going to be equal to, see that, 500 milligrams per liter times 1 over 78 times 10 to the third milligrams per mole. We end up seeing here that at 500 milligrams per liter, we have 0.0064 moles per liter. Okay? So let's see, now that we know how many moles we have and we know how many moles of oxygen are required for 1 mole of the benzene, then we can say that 0.0064 moles per liter of C6H6 times 7.5 moles of oxygen per 1 mole of benzene. And we can go ahead and multiply by that molecular weight of oxygen to get it in terms of milligrams per liter. So for oxygen, it's going to be 32, right? Because we have an atomic weight of 16, and we have 2 oxygens. So it's going to be 32 times 10 to the third milligrams of O2 per mole. end up getting there a concentration of 1,538 milligrams per liter. And so if you notice in the problem statement, it says the amount of oxygen that will be consumed to completely biodegrade the benzene is most nearly. So we don't have 1538 as an option, but we do see the closest answer there. That's going to be 1,600. So our answer will be D, 1,600. Okay? All right. Any questions on that? So you'll probably have something where you'll have to balance reaction and then use stoichiometry of that balanced reaction to determine concentrations. So this would fall under kind of that general water quality problem section of environmental engineering. All right, now let's look at BOD demand. So typically we're looking here in rivers, but for this question we're looking at wastewater flows that combine in a sewer. So for wastewater people in here probably remember this equation. It was remember this question. It was very similar to one they saw in their exam. So we have 3 wastewater flows that are combining in a sewer, each having flows in BOD concentrations as depicted here. So if we have infiltration, which has 0 BOD, so this is going to be percolation from the overlying soil into the pipe or into that sewer, and it's 10% of the total flow, wants to know what the resulting BOD is going to be. So basically this infiltration is going to be diluting the BOD, if that makes sense. So the way we go about solving this problem, we basically will be using a weighted average of the different sources. So we can say that our flow, if we want to calculate the flow rate, Q, it's going to be 4 times 10 to the 6 plus 0.8 times 10 to the 6 plus 0.2 times 10 to the 6 equal 5 times 10 to the 6 liters per day. Okay? Our infiltration is given as 10%, so 0.1 of that total flow. So times 5 times 10 to the 6 liters per day. So we see the amount of infiltration that we're going to have is 0.5 times 10 to the 6 liters per day. This means our total Q is equal to 5.5 times 10 to the 6 liters per day. Okay? So our BOD of the mixture is going to be equal to the sum of the individual BOD sources, BOD sub I, times QI, divided by the sum of QI, so our total flow. So here this is going to be equal, I'm going to drop the 10 to the 6 right now so I don't have to write it over and over again. It's going to be equal to 4 times 200. That's going to, and the concentrations, or the BOD there, I believe is given in terms of milligrams per liter. So 4 times 200 plus 0.8 times 300 plus 0.2 times 500. And to be complete here, to be comprehensive, I want to include that 0.5, the infiltration component, times 0. It has a BOD of 0. And we can divide all this by the total flow of 5.5. Okay? So we end up seeing here that we have a BOD of our mixture that's equal to 207 milligrams per liter. And so our answer there is going to be C. What if we, or B, sorry. What if we took, instead of dividing by 5.5, what if we divided by 5? So has anybody got a calculator there that they can calculate that? Multiply it by 5.5 and then divide by 5. 228. So I think that's going to be answer C there. So if you do not include infiltration, you could get the wrong answer there. Okay? Got to be careful with those kind of details. All right, any other questions on that? All right, so the last one we have to talk about here, it's a two-part problem. And the trick with this one is that you're given a lot more information than you need. So they try to overwhelm you with information here, and you got to cipher through what's important, what's pertinent to the problems being asked, and what's kind of erroneous additional information that we can brush aside right now. So we're told for questions 15 and 16 that we have a municipal activated sludge wastewater treatment plant with primary clarification. So this is going to be primary sedimentation. We'll be talking about this in class here in the next couple weeks with the following characteristics. So we know that as a flow, it's treating we have a flow rate here through the system of 5 million gallons per day. It gives us our BOD5 concentration at 200 milligrams per liter. We're given suspended solids, and then we're given some additional information about the normal operation of the facility. So the first question we want to answer here is if we have a plant BOD5 removal efficiency, so it can remove 95% of that BOD concentration, and the primary clarifier, so the primary sedimentation removes 35% of that BOD, then the amount of BOD5 removed in the biological reaction, so after we go through the primary sedimentation process, we're going to send it to activated sludge, and those microbes are basically going to break down that organic matter and remove that BOD. Okay? So it wants to know what the amount of BOD removed during that biological reaction is going to be. So the information we need here for this question, we're going to need to know the flow rate, the concentration of that BOD5, that 200 milligrams per liter, and I believe that's all we're going to need for that problem from this initial table. So we're given that we have a plant efficiency. So in total, the plant efficiency, or PEFF, is going to be equal to 0.95. Okay? The primary clarifier, we can call it P dot C, its efficiency is going to be equal to 0.35. Okay? So W, we'll use that term right now. It's basically telling us the weight of that BOD is going to be equal to Q times the concentration at BOD5 times a conversion factor. So here we have to use this conversion factor that we have 8.34 pounds per million gallon. Remember here, MGD is going to be million gallons per day divided by milligrams per liter. Okay? So we end up seeing here that this is going to be equal to 5 million gallons per day times 200 milligrams per liter. Go ahead and put that in there, that it's the units. Million gallons per day times 8.34, our conversion factor there. We ended up seeing we have 8,340 pounds per day. And so this is the the weight of BOD coming through that plant in a given day. So it's going to be 8,340 pounds in a given day. So our removal efficiency in that initial step, that primary clarifier, is going to be 35%. All right? So if our efficiency there is 35%, then we can see it's going to be 8,340 pounds per day. That's what's coming through there, times 0.35. Actually, let's do this. Let's look at how much is going to be. If we have 35% removed, that means 65% is going to be moving on to the activated sludge process. So we can say 1 minus 0.35. We'll call this going to activated sludge. Okay. So we end up seeing there that this value of what's removed there in the primary clarifier is going to give us 5,421 pounds per day that are going to the activated sludge process. Okay? And we also know that the amount that's leaving the plant, if it has a 95% removal efficiency, that the amount that's going to be leaving the plant is 8,340 times 0.05. So that means 5% of the BOD loading is leaving our plant. It's going to be equal to 417 pounds per day. Okay? So if we do a simple balance there and we say that 5,400 is coming in to the activated sludge and 417 is leaving the activated sludge, then we can say our removal, and it's just a simple mass balance approach here, and our activated sludge is going to be equal to 5,421 pounds per day minus 417 pounds per day. End up seeing that we have 5,004 pounds per day removed in that activated sludge process. Okay? Any questions on that one? So I know you guys haven't seen this yet, but we'll be talking about that more a little later in the semester. All right. So moving on, last one here. So it also wants us to calculate what the aeration basin volume is going to be in gallons. Okay? So here, if we go back to our original problem statement, we say that under this normal operation of the facility that the aeration basin has a hydraulic residence time of 10 hours. Okay, and we know what the flow is coming through that basin. So if we know what the flow coming through that basin is and what the residence time is, we can determine what the volume of that basin is going to be. Okay, so this is pretty much just using the flow rate identity in this problem. Okay, so we see here that flow rate is going to be equal to volume over the residence time. So we can rearrange that. See there that our volume is going to be equal to Q times T. So we know that the flow is 5 million gallons per day. And since we're working in gallons, let's go ahead and write out. We have 5 million gallons there. And we know that the residence time is 10 hours. Okay? So one thing to notice here, and if you don't do this, you'll end up getting answer D, is that you're given your flow rate in gallons per day, residence time in hours, you got to make that conversion. Okay? So this is an easy place to get tripped up on the conversion when you're trying to work fast. So we're going to have basically there, sorry, 1 day, 24 hours. End up getting there a volume of 2.083 times 10 to the 6 gallons. Okay, so 2,080,000 gallons. All right, so our answer there is going to be D. or C, sorry, yeah. All right, any questions on that? I think that's all I got for you today. So again, remember, if you have any questions or any specific problems that you're struggling with or need some help on, feel free, or you want an explanation on it, feel free to come to my office or shoot me an email, and we'll work through them. So, all right, thank you guys. Good luck on it.